Okay, everyone. So this is my second video dealing with harmonic oscillators, and we're actually going to take a look at what we call damped oscillators, and also we're going to I'm going to show the relationship between simple harmonic oscillators and objects undergoing uniform circular motion. So real quick, everyone, just to say again, we see here. Let me move this thing out the way. Something underneath the computer here. So you see at the front table, you of course remember this again, the harmonic oscillator that we used in lab. And everybody, technically that was a damped oscillator. Damped oscillator, everybody, means this. As the object moves back and forth, its motion is going to decrease with time. And the reason why the oscillator is damped it's because of outside forces such as friction. Because you have energy loss due to friction, as well as the fact that the springs are not ideal. The springs themselves will heat up over time, and they will gradually lose energy as a result. Let's say again, maybe if you have a very fast moving oscillator, wind, or a very large moving oscillator, wind might have play a role as well, or air resistance, to slow your oscillator down. So oscillators can be damped all kinds of ways. But everybody, the word damped, in this sense, everybody basically means this. The motion undergoes a decrease as time goes forward. Now, a driven oscillator is one that if you use the external force to keep the object moving or keep the object oscillating, that would be a driven oscillator. I'm going to share, let's say again, example of a driven oscillator in my next video. I'm also going to play around with, let's say again, a pendulum, or like a series of pendulums, pendula, that's a proper plural form. I'm going to deal with a series of those in this video as well. But still, everyone, let's go ahead and look at this. So we got a simple harmonic oscillator at the front table, and everybody on my phone here, I'm going to be using data read in from the wireless sensor that's attached to the a spring card or to the card or dynamics card at the front table. So I'm gonna hit collect. All right. Now right now it's not gonna read anything because there's no motion. But everybody, once I actually pull back the card and let it oscillate, take a look at what's going on the screen. And everybody, it's kind of hard. The color it shows is kind of hard to see on the camera, everyone. But if you can see, like say, again, those lines mapped out on my phone. Those lines basically, everybody, show that this object is indeed undergoing subharmonic motion. And actually, technically, what I'm measuring is acceleration. So not only do you have a sinusoidal pattern to the position versus time, but also you have a sinusoidal pattern to velocity and acceleration. For those of you who have to take calculus-based physics later on, or have to deal with that later on, what happens to everyone is that velocity, remember, is the derivative of position, and acceleration is the derivative of velocity. So what happens is you have a series of, I'll say again, sine and cosines, which one of the equations for position, velocity, and acceleration. Okay? And let me actually do this again because that color didn't show up very well on the camera, at least not from my vantage point. So I'm going to do this again. And maybe this time we'll choose a color that's a lot more suitable for the camera. But the thing I want to, again, to point out to everybody is this. Notice how everybody, as time goes forward, the motion decreases. That means that the acceleration, as you'll see, is going to decrease. And so everybody, what happens is this situation, the motion is damped, and we see what we call an attenuation of the on the graph. In other words, that's just a fancy word meaning that the motion is decreasing, and therefore the peaks are getting smaller and smaller. So we see as time goes forward, indeed, the motion decreases and it is coming to a stop. Now, so I'm just going to go ahead and stop that because we know what's happening here, or what's happening now. Now, everybody, let's do this again. But this time, I'm actually going to turn my camera around here. All right. So everybody, what I did this time is, you see this apparatus from across from my camera now. What happens, everyone, is that this is a rotating apparatus, first of all. And second of all, say again, I have a laser on top of it. And that laser is standing at a fixed distance away from some axis of rotation. So this thing is going to spin around, and the laser is going to be, the laser beam is going to be, say again, shining. And what happens is it's going to cast a dot on the wall. So I'm going to turn the lights off, and what I want you to do is watch the motion of the dot as the apparatus rotates around. So let's go ahead and turn the lights off here. First of all, let's say again, while I'm getting the lights together, everybody, you see this little, funny looking thing. That's actually a torsion pendulum. And I'm actually going to demonstrate the torsion pendulum in this video as well. But let's turn the lights off. Okay. And I'm going ahead and get this thing spinning. Okay, it's going very fast right now. But everybody, take a look at that, again, that pattern being cast on the wall. Okay? And I have the laser purposely pointing up to basically amplify the effect. Okay? But everybody, what happens is that uniform circular motion and some harmonic motion are both periodic motions. Okay, they vary. Like say again, with they have like say again with time. What happens is you have a repeating pattern with them. With say again as time goes forward. So let's do this again. Match out the stabilize the camera here. And match thing going again. We actually you got a little bit, lean a little bit. Okay. Now let's rotate the scan again. Get this on camera. So again, everybody see that pattern. When you project uniform circular motion in 1D, you get a similar pattern or the same pattern as you do with some harmonic motion.